In the third example for scientific notation, we're being asked to sum two different numbers written in scientific notation with different exponents. So the different exponents come from the fact that we have the 4 here and the 3 here. So there's one way we could do this. We could convert both of them to standard notation and then sum them normally. So just doing this really quickly, this first number would represent 34,200, and the second number would represent 2,610. And we can sum these normally. We know how to do that. I'm not going to do it this way. I just wanted to show you that this possibility existed. What I'm going to do is, I'm going to convert one of them so that it has the same base 10 power as the other one. So I'm going to choose this first number here, and I'm going to make it be base 10 to the power of 3. So what I'm doing here is times 10 to the 4 minus 1. And if they both have the same 10 to the power of, then they can just be added normally. If I subtracted 1 from this 10 though, I'm violating a math law right now. So what I need to do is, since I basically divided by 10 here, I need to multiply by 10 at this part here with the 3.42. So in multiplying by 10, I'm moving the decimal place 1 to the right. So I have 34.2 times 10 to the 3, which is what I want. And the second one can stay the same for now because it already has the exponent that I'm looking for anyways. So in rewriting this, I now have 34.2 times 10 to the 3 plus 2.61 times 10 to the 3. Now I can add these. 4.2 times 10 to the 3 plus 2.61 times 10 to the 3. And I can add these normally. So I can make this a 0, it's just a placeholder. And I can sum the hundredths, they give me 1. Sum the tenths, I get 8. Make sure your decimal place is always lined up. And then sum the ones digits, you get 6. And then this, 36.81. And this is still times 10 to the 3. This is just like a factor here. Okay, so I have that. Now, this is not my final answer, because the rule of scientific notation says that the decimal has to exist after the first significant figure. So my 3 is the first significant figure, the decimal is not there. So I've got to manipulate it a little more. And in this case, I need to move the decimal place this way, 1 to the left. So basically what I'm doing is, I'm dividing by 10. So I have to do the exact opposite when I've got the 10 to the power of thing to make up for it. So essentially, what I'm doing here, I'm adding 1 to the exponent. So this is multiplying by 10. This was dividing by 10. Any number divided by 10 times 10 is itself. So that's good. I haven't changed what this represents, and I'm following the rules. So, to finish, my final answer is 3.681 times 10 to the 4. And that's my final answer. So to summarize, just briefly, the first thing that I had to do was to change the exponents so they are the same. That's what I did with all this business up here. Second step, I can sum them. Sum the bases basically, leaving the 10 to the x factor. So basically that was my 10 to the 3. I'm just saying x can be any digit. And finally, third, move decimal to ensure it is after the first significant digit. So this was step 1, and then this whole business was step 2, and then all this stuff I did over here, that was step 3.